Hello. So in this video, I'm going to just introduce why we might want to estimate flood frequencies using normal distributions or other probability distributions. So I'm going to start just by talking about the Sacramento River. And I apologize that this image of the Sacramento River watershed didn't transfer over very well, but you can basically see the point that I'm trying to make here with this image, that the Sacramento River drains a very large area of California. So it starts way up north. In fact, the watershed for the Sacramento River begins in southern Oregon, and it drains through Sacramento and then into the San Francisco Bay and Delta. And so, as you can imagine, a river gets wider and has more flow capacity and needs to hold more flow as it gets further downstream. And one of the places that is impacted by floods on the Sacramento River is the city of Sacramento. And part of that reason is because if you look closely, you'll see there's another very large river here. It's called the American River. It's here, and it discharges or joins up the confluence, that's the word used, of the American River and the Sacramento River is right near downtown Sacramento. And so the section of the Sacramento River downstream of that has a very large capacity. So the consequence is flooding. And so Sacramento is the capital of the state. But when it was first being established, Sacramento flooded frequently. So there's a part of Sacramento called Old Town, if you've ever been there, and that used to flood frequently. It's right near the river, and so they eventually had to move the capital. But on this bottom picture here, there is a picture from 1862 when there was a very horrific flood that occurred in Sacramento. Okay, so it's clearly not a picture, but an illustration. And on the top is a picture of the Sacramento River looking towards West Sacramento. And you can see what's called the Tower Bridge here. And so this shows very close to flood stage conditions on the Sacramento River. But over the years, many flood control projects have been built to help to decrease overtopping of the river into downtown Sacramento. But it is still possible to have flooding in downtown Sacramento. Okay, so this is a river that has historically flooded many times, but we have urbanized the area very close to the river. And so we would like to be able to make sure that we're providing a level of protection to minimize the risk of flooding, therefore minimizing the cost of having to fix a flooded condition. So here's some data, and this data is showing the years and then the maximum flow rate in each of these 70 years that occurred at the Sacramento River, and this is downstream of the confluence of the American River. Okay, and so we're going to look at different ways that we might analyze and look at this data. So one thing I do usually when I get data is I just plot it. So here I have each year and then that maximum flow rate. And this doesn't really tell us very much. I can see that there are years when there's a lot of flow, and then I can see there's years when there's not a lot of flow, but I don't see any real patterns. And I can't use this to really assess what my risk is in building near the Sacramento River, right? So we need a different way to look at and analyze this data. So another thing I can do is I can take all that data and I can create a histogram. Okay, so what I've done here is I've created bins which have a max and a min range, and I count how many times I have a flow in each of those bins, and then I plot it as a bar chart. And this gives us a little bit more information, right? So what does this tell us? This tells us that of the 80 years of data that I had, or 70 years of data, the highest percentage of flows occurred in this bin, so around 1400 CFS, okay? I only had one time where I had a flow this low, and I had 4 times when I had greater than about 2400, 2500 CFS, right? So this starts to show a little bit better of a pattern of what we can expect the flow to be in the Sacramento River, downstream of the confluence with the American River, and will help water managers to be able to build um, build structures to help maintain flood protection. The last set part of this module presented a different way that we could look at this data, right? So this is an approximation of a probability plot. It's not done on Weibull plotting paper, but I've still done the same procedure where I've listed all the flows from the highest down to the lowest and calculated the probability of non-exceedance and the probability of exceedance. And again, this can give us some general sense of the risk associated with the flows, okay? But there are some caveats here. These estimates assigned to the large floods are highly inaccurate, and the same is true for low flow, so drought conditions. Okay, so this Weibull plotting position works really well for what happens sort of in the middle in the mean or the median values of flow, but it doesn't work at the extremes. But as flood managers, we really are interested in what happens at those extremes. So this method loses its validity pretty quickly. Okay, so I'm going to come back to this histogram because I want you to notice sort of the shape that it's taking, right? This is not perfect, but it is starting to look a little bit like what we know as a bell curve, right? And so we're going to make some assumptions here that flow in a river, maximum flow on, say, a yearly peak flow each year, can follow a probability distribution, okay? So we're going to start by looking and making an assumption of that the flow at the Sacramento River is normally distributed. So on that note, I went ahead here and I calculated the mean. We sometimes see this as mu or mu prime or x. Okay, so we have the mean. We have the standard deviation. This is sometimes shown as sigma or s prime, say all the same thing. And then this last one is the skew, and we will get to that. You'll watch a video from a professor at Cal Poly Pomona that explains the skew, okay? So I've calculated what are known as descriptive statistics, the expected value, which is the measure of the central tendency of the data, right? And then the standard deviation, which gives us a little bit of information about the variation or the spread, and then the skew. And the skew is a measure of asymmetry of our probability distribution. So I'm going to draw here a normal curve for our Sacramento River data. Okay, so I'm going to have flow or Q, peak flow, on the x-axis and a probability on the y-axis, okay? And I'm going to, we're talking about water, so let's draw our normal distribution in blue. And so this is going to look something like this, right? And what do we know about this curve? We know that this top part here, the maximum basically, is our mean value. So I can write that as mu or q prime, and it is equal to 1179. Okay, what else do I know? I know I can put over here one standard deviation away, right? So this is one standard deviation, and then we can calculate to the next point to 2 times s. We know this information from learning about normal distributions, and so this would be a flow of 1701, and then this more extreme value would be 2235. And we can do the same thing on the other side. Okay, we can indicate where one standard deviation of flow occurs, and that would be at a value of 651 CFS, and then at 2 standard deviations away, we would be at 123 CFS. Okay, and what else do we know? We also know from learning about normal distributions that 68% of our values are going to occur within 1 standard deviation of our mean. Okay, and then if you extend that, excuse me, to 2 standard deviations from your mean, you're going to capture about 95% of all of the values. And so we're going to use this standard normal curve and standard normal distribution tables to help us to estimate the probability of exceedance and non-exceedance for flows. And so the next thing I would like you to do is watch the videos I posted by Dr. Lamb from Cal Poly Pomona, and then tomorrow during our class time, we will talk through some examples of this and work through working with our standard normal curves and standard normal tables.